Okay, everyone, so we're going to be looking today at galvanic cells. Galvanic cells go by several different terms, electrochemical cells, galvanic cells, a voltaic cell. They all kind of mean the same thing. We're looking at essentially a battery, okay, or essentially how are electrons produced that we can use to do some work for us, such as lighting a light bulb. Okay, so we're going to do a little bit of a quick review of redox reactions. So just a reminder that a spontaneous redox reaction or oxidation reduction reaction is where you have electrons that are transferred. So what happens is you have an oxidation reaction where you have a loss or a losing electrons, and then you have a reduction half reaction where you have a gain in electrons. So electrons are transferred from the item that is being oxidized to the item that is being reduced. So what we can do is we can have those electrons transfer through an external device, such as a conducting wire, and have those electrons do some work for us along the way. So we can use that for use its potential energy. And we're going to look at how do we know how much potential energy electrons have, how do we know if it's spontaneous or not. So we'll look at that throughout this section. So electric current is produced when electrons are flowing in a circuit, of course. So electrons have to be produced, they have to be moving. So the device that we can use to take chemical energy and convert it into this flow of electrons is called a galvanic cell, or a voltaic cell, or an electrochemical cell. So if you remember way back to grade 9 days, you know that this is essentially the same thing as discussing a battery, right? So it's a source of electrons, right? So we're looking at essentially what is the chemical reaction that is happening inside of a battery, and how can we use those to be set up, those electrons, to do some work for us. So I've already mentioned this, what this cell says, what this slide says. So electrons are transferred from the substance being oxidized to the substance being reduced. The reactants can be arranged so that the electrons are transferred through a conducting wire. So we want those electrons to be transferred externally. So how do we do that? So we do this by actually setting up the oxidation and reduction half reactions in two separate containers. So we call those containers half cells. So in one container, let's say a beaker, right? So let's say we're making a crude battery. In one beaker, we would have a reduction half reaction happening. In a different beaker, we would have our oxidation half reaction happening. So we call them half cells because when they come together, they really will make one electrochemical cell. So we have our oxidation half cell, our reduction half cell, and then working together, we can get our galvanic cell or electrochemical cell, which is essentially what was mentioned here. So the two half cells will be joined so that the path is provided for the movement of electrons, right? So we're using a wire, and we haven't seen this yet or discussed this yet. This will make more sense once we look at some diagrams of cells. We will also be creating an alternate pathway for ion movement. Okay, so ion movement will become important, especially if we want our cell to continue running. Okay, again, I'll mention this and we will bring this up again when we look at our diagram and look at that ion pathway. But essentially, you have to have a method of electrons to be moving from one cell to another, and you have to have a method of having ions moving from one cell to another. And of course, the two half cells, once they are combined, will make up our galvanic cell. Okay, so here is a typical diagram of what a galvanic cell looks like. Okay, so first of all, let's look at the way that this is set up in terms of equipment. So notice we have one beaker and then another beaker that are separated, right? So these are representing our two half cells. Okay, so that means one cell has oxidation, the other cell has reduction happening. So the two cells have a liquid component, so it has a solution inside, and also a component of a solid piece of conducting material, okay? So you have like basically a metal and a solution, another metal and another solution, okay? Obviously, the solution that is inside of this container and the metal that is chosen will depend on the reaction that is happening at that particular half cell, okay? The two metal pieces are connected with conducting material. So this is the electron pathway that we were talking about before. So the electrons always flow from where they are lost to where they need to be gained. That should kind of make sense. If they're being lost here, they have to be transferred to where they're going to be gained. So the flow of electrons will depend on which cell is which. So this center portion, you'll notice there's kind of like, this is usually made out of Pyrex glass. Okay, so this is that pathway I was mentioning for ions. Okay, so we have an ion pathway, we have an electron pathway. And actually, those are the only two things that are connecting the half cells to one another. So we're going to kind of dissect down what each of these parts are. Okay, so first of all, let's look at the reactions that are happening. So on the left side, we can see the half reaction that's occurring. So we have solid zinc becoming zinc ions. And of course, to do that, there is a loss of 2 electrons. So remember that Leo the lion says grr. So since this left side beaker is where electrons are being lost, that tells us that this is our oxidation half cell, right? Now, it doesn't always have to be on the left side. You have to look at you have to understand, well, what reaction is happening in this half cell? So here we're losing electrons. In this other half cell, we have copper ions gaining 2 electrons that are creating solid copper. So in this case, so again, gaining electrons is reduction. So that tells us in this half cell is our, oh, I couldn't grr, but that is our reduction half cell, right? So electrons are lost in this portion, and that's also why we have the electron movement here, and they are gained in this portion. Now, the metal pieces that are in our solutions have terms. They're actually called electrodes. So all the stuff I'm talking about here on this one picture, we will go through again on the next upcoming slides. So these are electrodes. Okay, so you have a solution, which are called electrolytes, with ions in solution, and electrodes. Okay, that might even sound familiar from when we learned about batteries back in grade 9. So the electrodes are very kind of like a generic term. Like an electrode means basically a metal in a solution. But depending on what type of electrode it is, will depend on what half cell it's located in. So the electrode that is in the oxidation half cell is called the anode. So notice here that we are calling this piece of zinc the anode. So before I continue on, actually, I want to explain why is this zinc here. So the metal is typically the metal that is involved in your half reaction. So here we have solid zinc, that's a reactant. So that is why we're using solid zinc. Over here, copper that is solid is part of our half cell for reduction. So that is why solid copper is chosen here as the electrode. The solution has to contain the ions in this reaction. So this solution has to contain zinc positive 2. This solution would have to contain copper positive 2. We'll look later on. There are going to be some instances, well, like what, for example, what happens if there is no solid in that half reaction? We will look at different circumstances for that. For now, the solid is typically whatever solid is in your half reaction. The component the aqueous component must have the ion that is in your half reaction. Okay, we'll look at this centerpiece in a little bit. Okay, so we have our anode is our kind of label for the electrode in the oxidation half cell, and the electrode that is happening or that is placed in our Reduction half cell is called the cathode. Okay. So to try and help you remember which is which, I kind of add on a letter to the end of our Leos. The lion says ger. So I add on an A. Leoa. Losing electrons is oxidation at the anode. So A for anode. The anode is always in the oxidation half cell. Gaining electrons is reduction at the cathode. So it's now kind of like Leoa and Girk, or however you want to remember that, okay? So no matter what, you need an electrode in each half cell. The label at which that electrode is, of course, depends on, well, what half cell reaction is occurring there. Okay, so far we've gone over why we have these ions, the terms here. So we're going to look a little bit deeper. Let me just clear this out. I like this diagram because it's nice and big for us to look at. Actually, yeah, we're okay. I'm going to clear from the start. Okay, here we go. Okay, so we've talked about the ions. Now let's talk about the movement of the ions in the beaker. So we're not going to look here yet. We're going to look at the beaker. Okay, so the process that which is happening will kind of dictate what is happening in solution. So for example, here we have solid zinc becoming zinc ions. So notice there is an arrow coming off of this solid piece and showing that the zinc ions are in solution now because of it. So solid zinc is becoming zinc ions. Over here, we have copper 2 ions that are becoming solid copper. So notice there's an arrow showing that the copper ions in this solution are going on to this copper metal piece because we're essentially making more solid copper. So over time, the electrode will actually change in mass. So meaning, let's say we were to weigh out these two electrodes before running this cell. What would happen over time is this zinc piece will eventually become lighter and lighter. The reason why is because the atoms in that solid piece are becoming ions. They're going into that aqueous solution. So let's say we were to run this for maybe 5 hours and weigh it at the end, you will see a mass change in this solid piece. Now, it's not going to be so quick as to, it's going to disintegrate and disappear on us. You have to remember there are, trillions and trillions and trillions of atoms in this single little piece of zinc. So even though you do have ions coming off of this, you may see a change in mass of maybe 1 gram or even a half gram. You're not going to see a huge difference where it's like the naked eye would not even be able to really see it. You'd have to use a scale to measure the difference. Now, the opposite is happening over here. We are using copper ions in solution to create more solid copper onto this electrode. So over time, what's happening to the copper is it's actually getting heavier and heavier. So again, same reasoning. You're not going to be able to see this with the naked eye. You turn around 30 minutes later, you come back and there's like an extra big chunk on there. But if you were to let this run for a little while and weigh it before and after to look at the difference, you will make note that there is more mass on that cathode because you're creating solid copper. So when you're looking at, this is not a generic thing. So I don't want you to remember, the anode always decreases in mass, cathode always increases. This does happen most of the time, but you really have to look at the half cells to kind of understand the process that's occurring inside of that cell.